Okay. So, hi everyone. Thank you for being here today. So today, we have Dr. Sejong Kim from Chungbuk National University, Korea. He's specialist on least square means, and he has a lot of papers on this topic. So, I hope you enjoy it. So, his talk is least squares means and the extensions. Please, yeah.
Yeah. Um, First of all, I would like to thank to Hoa to invite me and give me this opportunity of talk at Trojan Math Seminar. Today I'm gonna talk about my research interest, which is the least squares mean of positive definite Hermitian matrices, and finally we discuss their extension to positive operators. Actually, it is a long-standing problem to define a barycenter, or sometimes named a mean of a finite number of points in a given metric space. A natural and canonical mean is the least squares mean, which is a minimizer of weighted sum of squared distances to given variables. The originate is actually introduced by the Frechet, so we sometimes also call it Frechet mean. But it is difficult to say the existence and uniqueness of such minimizer. Several years ago, German mathematician Carl has shown that the least squares mean uniquely exists on a Hadamard space. The Hadamard space is the complete metric space satisfying the semi-parallelogram law. The following inequality is a semi-parallelogram law, which is that the sum of squares of the diagonal lengths is less than or equal to the sum of squares of all sides. Indeed, in this inequality, the point M plays a role of the midpoint of A and B.
Wait a second. I think
Yeah.
your slide is not moving.
Oh, really?
We can only see the first slide.
Okay, then.
Sejong, it might help if you go to full screen because it shows like a reader, PDF reader, but if full screen, it will change slides.
Okay.
Control L, I believe.
It works now?
Well, we only see the first slide, the title, and then nothing was changing.
Okay. Now it's moving?
No.
No.
No?
Like I said, try to go to full screen mode.
Well, I did full screen.
I think that's the reason. And full screen opens in a different window. So what you're sharing is not full screen window, but the slides window. That's why we cannot see them.
What about this?
Oh, yeah,
now it's not full screen, but we can see fresh aim in.
Okay. So can you see now the next slide?
Yes.
Yes.
Not in full screen, but yes, we can. Yes.
Yeah. I think full screen doesn't work.
No, it does, but it opens a different window, and you're sharing not the window with the full screen, but the window with the PDF reader. So what you could do, you could close this one and open the full screen. Like there should be stop sharing button or the X in it or something.
Okay, I close the slide and share again.
Mhm.
And I'm now moving the slide. Can you see or not?
No, just the first slide.
Okay. Then I think I'm using different program, Adobe Reader. So I think just to click
Yeah,
the
yeah.
next
Okay.
slide.
It changes now. It changes.
Yeah.
Yes.
Okay. All right. So then I think I have explained the Fletcher mean, the least squares mean, and so let me skip this. Is that okay? So it's the introduction of the least squares mean, which is a minimizer of the weighted sum of square distances to given variables. And several years ago, it has been known that on a Hadamard space, the least squares mean uniquely exist. So in my talk, we consider such least squares mean of positive definite matrices. So in the following, I denote as P capital P sub M, which is the open convex cone of all m by m positive definite Hermitian matrices. And it is known that for two Hermitian matrices, we have a partial order, and two Hermitian matrices, A and B, A less than or equal to B if and only if B minus A is positive semi-definite. A is strictly less than B if and only if B minus A is positive definite. And this is known as Lubner partial order. And there are two remarkable properties about the Lubner order. The first one says that the inversion map is actually order reversing. And we have a congruence transformation, which is A from A to S A S star. And then second property says that a congruence transformation is order preserving. And for the any invertible matrix S. For the simple example, I will introduce the arithmetic mean. So now we consider the open convex cone P sub M equipped with the Euclidean distance. So for 2 points A and B, D sub E of AB is given by the Frobenius norm of A minus B. So it is actually complete metric and also satisfies parallelogram law. So our setting here is a Hadamard space. So we have a unique minimizer of weighted sum, which means the least squares mean uniquely exist. So now what is that? It is actually coincide with a multivariable arithmetic mean, which is the weighted sum of Wj and Aj. And how can it define the harmonic mean? So harmonic mean and arithmetic mean has like a dual. So harmonic mean is defined by inverse of weighted sum of variables Aj inverse. Now let us consider in the same space P sub M equipped with the different metric. So I denote it as D sub log. So for given 2 points A and B, D sub log of AB is given by Frobenius norm of log A minus log B. And it is known that exponential map from the real vector space of all Hermitian matrices H sub M with a Euclidean distance to the open convex cone P sub M equipped with D sub log is isometry. So using this fact, we can see that D sub log satisfies parallelogram law. So in this setting, what is the least squares mean? It is actually multivariable log Euclidean mean. That is given by exponential of weighted sum of log aj. There is an interesting property about log Euclidean mean. If the variables commute, then log Euclidean mean is exactly product of aj to the power wj. That is a scalar version of a geometric mean. So until now, we have seen arithmetic mean and log Euclidean mean. And how can we construct multivariable geometric mean? Log Euclidean mean can be one of the kinds of multivariable geometric mean, but unfortunately, it does not satisfy the monotonicity. In the sense of Kubo and Ando's operator mean, monotonicity property is very important, but the log Euclidean mean does not satisfy. So we need another geometric structure. So let us consider Riemannian structure. So at a given point A, we can consider the tangent space at a point A, and it is actually identified with a real vector space H sub M. And we have a natural inner product there. So for two tangent vectors, x and y, at a point A, their inner product is given by trace of A inverse x, A inverse y. So using these inner products, we can compute the norm of tangent vector. So norm of tangent vector x at a point A is given by square root of inner product x and x. So using a simple matrix analysis, we can see that the norm of tangent vector is coincide with the two norm of a power minus 1f x, a power minus 1f. And so using this norm, we can compute the arc length of a differentiable curve, which is integral from 0 to 1 for the given curve gamma. So arc length is given by integral from 0 to 1 of the norm of tangent vector gamma prime t. So there are several differentiable curves connecting 2 points A and B. So Riemannian distance between 2 points A and B is defined by infimum of all arc lengths L of gamma, where gamma is the differential of curves connecting 2 points A and B. And using basic matrix analysis tool, we obtain the explicit form of Riemannian distance, which is Frobenius norm of log a power minus 1f b a power minus 1f. This is called Riemannian trace metric, or simply we say trace metric. And also, we can find a unique geodesic formula connecting A and B. Their formula is given by a power 1/2 times t power of a to the power minus 1f b a power minus 1f and times a power 1f again. And this is known as two variable weighted geometric mean of A and B. We also denote it as A sharp TB. For the case t equals 1/2, we simply write it as A sharp B. And also one can see that two variables commute, AB equals BA, then A sharp TB equals A to the power 1 minus T times B to the power T, which is a scalar version of two variable geometric mean. And the previous two slides actually appeared in Rajendra Bhattia's book, Positive Definite Matrices. And in there also, one can check that the open convex cone P sub M with a trace metric is Hadamard space. So we have a unique minimizer of weighted sum. So we call it the Cartan mean and denote it as capital lambda. Moreover, our objective function, which is a weighted sum, is strictly convex. So by optimization theory, we can find the Cartan mean by vanishing the gradient of objective function. Then we can say that Cartan mean coincide with a unique positive definite solution x of the following equation. So weighted sum of log x to the power 1/2 aj inverse x to the power 1/2 equal to 0. This is called the Kacher equation. So in this sense, some people says Kacher equation. Kacher mean. As I know, in 2003, the first attempt to construct multivariable geometric mean is introduced by Ando-Lee-Matthias symmetrization process. So the symmetrization process is construct nested sequence of triangles for the given 3 points, and they show that the sequence converges a single point. So it is a 3-variable geometric mean. So inductively, we can define the n-variable geometric mean. And in the same paper, they suggest 10 properties for a certain map. In this slide, the map is G, to be a weighted multivariable geometric mean. So let me introduce their desired properties. So the map G here, so delta n, which is a simplex of positive probability vectors in Rn, Cartesian with Pm to the power n, 2Pm, is weighted geometric mean if this map satisfies the following properties. The first one says that consistency with scalars, which means if variables commute, then their map G is the product of AI to the power Wi. And second property is the joint homogeneity. So we multiply positive scalars on each variable AI, and their map G is equal to geometric mean of positive scalars AI times map G of original variables. Third property is permutation invariance. So we take a permutation on the weight omega and permutes the variables, and their map G is actually G of original variables. And fourth property is monotonicity. So if variables bi is less than or equal to ai for all I, then map G of bi less than or equal to map G of ai. Fifth property is continuity. So the map G is continuous on variables. And actually, if the map G satisfies joint homogeneity and monotonicity, then the map G is contractive for the Thompson measure. And this is shown by Lim and Parfia. And sixth property is congruence invariance. So we take a congruence transformation on variables. Then their map G is equal to the congruence transformation on G of original variables. Seventh property is joint concavity. So we take a convex sum of variables ai and bi, and their map G is greater than or equal to convex sum of two maps, G of AIs and G of BIs. And eighth property is self-duality. So we take the map G of the variables AI inverse. That is equal to inverse of the map G of original variables. Ninth is determinant identity. So we take the determinant of the map G of the variables AI is equal to the geometric mean of positive scalars determinant of AI. And the last one is arithmetic geometric harmonic mean inequalities. So these are the Anderle-Matthias 10 properties of the map G to be a weighted multivariable geometric mean. Indeed, the Cartan mean satisfies all these properties. Actually, the monotonicity is very difficult to show, but I think 10 years ago, several mathematicians have shown that Cartan mean satisfies also monotonicity. And there are two approaches to find the Cartan mean. The first one is the matrix power mean. We denote as P, capital P sub t, for the parameter t in between 0 and 1. P sub t is defined as the unique positive definite solution x of the equation x equals weighted sum of x sharp t aj. So how can you show this? We can just use a Banach fixed point theorem with a Thompson metric d sub t. It's given by operator norm of log a power minus 1f b a power minus 1half. So actually Thompson metric is a complete metric. So the right hand side here in this equation is a contraction for this Thompson metric. So using Banach fixed point theorem, we have a unique fixed point. And for the negative t in between minus 1 and 0, we can define the power mean p sub t using a certain duality. And there are two remarkable results about this power mean. So power mean p sub t converges to the Cartan mean, capital lambda, as t goes to 0. Moreover, for the two parameters s and t satisfying s less than or equal to t, then their power mean also satisfies the same order property. So this inequalities, chain of inequalities, is monotonicity for the parameters. So 2012, Yongdol-Lim and Parfia have shown this on the setting of positive definite matrices. And after 2 years, Jimmy Lawson and Yongdol-Lim extended these results to positive operators. And second approach is the no-dice theorem. So for given finite probability vector omega, we denote omega bar, which is infinite dimensional vector. We can just simply duplicate the entries on omega. And we denote the notation S of n, which is the sum of the ith entries of infinite dimensional vector omega bar from I equals 1 to n. Then we consider the sequence of weighted inductive means. The first term is given by the initial variable a1, and Sn is defined as ak sharp Sn minus 1 with the weight Sn minus 1 over Sn. So now how can it take the letter k? K is chosen so that kn equals n modulo little n. Then the result says that the limit of the sequence of inductive means Sn is the Cartan mean. So 2012, John Holbrook shown this result on the setting of positive definite matrices. And after 2 years, Youngdol-Lim and Parfia have extended this result on the setting of Hadamard space. For your understanding, let me give you a much more simple example about the inductive mean. So we consider n equals 3, and we consider the probability vector omega is a uniform probability vector. So entries are all 1/3. And consider the variables a1, a2, a3. And then little s of n is the sum I equals 1 to n of these entries. So we get n over 3. And then the inductive mean is given by the first term is a1, and second term is a2 sharp a1 with the weight s1 over s2, so which is simply 1/2. And s3 is given by a3 sharp as2 with the weight s2 over s3, which is 2/3 simply. And then replace s2 by a2 sharp a1, then we get the right hand side here. So now what about s4? So 4 is equal to 1 in the modular 3. So s4 is given by a1 sharp s3 with the weight 3/4. So we construct these inductive means in this manner, and the result says that this goes to the Cartan mean of 3 variables. And several years ago, I have found other interesting properties. So let me introduce their properties. The first one says that tensor product of 2 Cartan means on the variables ai and bi equals Cartan mean of the variables ai tensor bi. So the main idea of this proof is using Nordice theorem. Second property is that we consider n permutations, sigma 1 through sigma n, satisfying the set of sigma 1j through sigma nj is equal to set of 1 through n for each j. So we take the permutations on only variables and compute Hadamard product. Then it is less than or equal to Hadamard product of original variables a1 through an. Also, there is a lower bounds with inverse. Another property is that extended version of Lee-Trotter-Carter formula. So we take the s power on the variables ai, and we compute the Cartan mean and take the power 1 over s. And we compute the limit of this as s goes to 0. It coincides with log Euclidean mean. So this is, it actually 2 variable Lee-Trotter formula is well known, and this is a somehow multivariable version of Lee-Trotter formula. So if you are interested in these results, I give you the 2 references, 2016 and 2017. And there is also a unique characterization of Cartan mean. So previously, we have seen the weighted multivariable geometry mean satisfying Andoli-Matthias 10 properties. Moreover, if the map G satisfies the following, the weighted sum of log aj is less than or equal to 0, implies G of the variables ai is less than or equal to identity. So if the map G satisfies this property, then the map G is exactly the same as Cartan mean. So 2012, Yamazaki has shown this result. of the finite variables. And 4 years later, I extended this result to probability measures. By Carl Stum, German mathematician, he has established Cartan barycenter of probability measures with a finite second moment. So what is the definition? So given probability measure mu with a finite second moment, we denote capital lambda of mu, which is a Cartan barycenter, is defined as a unique minimizer of the integral of squared trace distances over mu. So if mu is a finite supported measure, then lambda of mu is exactly the Cartan mean of finite variables. So this is somehow extension of Cartan mean to the probability measure. And my result is that we consider invariant barycenter defined on the set of all probability measures with a finite second moment and satisfying this property. Also, this property is somehow extended version of finite case. And then the result is G of mu is equal to the Cartan barycenter. So what is in this statement, what is the invariant barycenter? Simply, it is a mean and invariant under inversion and invariant under congruence transformation. And we simply say invariant barycenter. And what is the operator extension of Cartan mean? So it is actually established by Jimmy Lawson and Yongdo Lim, 2014. So I would like to introduce their consequence. So in this slide, we denote B of H, the Banach space of all bounded linear operators on a Hilbert space. And we consider capital P, the open convex cone of all positive definite self-order joint operators. And their first result is that the power mean exists uniquely using the same arguments on the setting of positive definite matrices. And such power mean P sub t converges to the 2 points as t goes to 0 from the right and from the left in the strong operator topology. So they actually show that the power mean converges as this limit. So I just denote it as lambda plus and lambda minus. Moreover, the limits lambda plus and minus satisfies the Kacher equation. And their second result is that the following statements are equivalent and also satisfies for lambda plus. So what is that? The first one is lambda plus is joint homogeneous. Second one, lambda plus is contractive for the Thompson metric. And third one, the equation x equals lambda plus of x sharp TA1 through x sharp TAN has a unique solution, positive definite solution. And the last one, the set of all positive definite solutions of Kacher equation is a singleton, whose element is lambda plus. And previously, we have seen that lambda minus also satisfies Kacher equation. So using this equivalent statement, we conclude that lambda plus is equal to lambda minus. So the Kacher mean of positive definite operators can be defined as unique positive definite solution of Kacher equation. And also the power mean converges to a single point, which is the Cartan mean. So this is operator extension of Cartan mean. And so one can ask that why we don't consider Riemannian distance, because on the setting of positive operators, there is no such Riemannian trace distance, and also no non-positive curvature metric. So we cannot adapt the optimization setting, like a minimization. So then their idea is to solve the Cartan equation. So that's their main idea. Okay, so from now, let me introduce another least squares mean. This is a very the recent topic and very hot topic actually. So just a couple of years ago, Bhatia and other mathematicians introduced a new Riemannian metric, and they are named Wasserstein metric. And also they established the least squares mean for this Wasserstein metric. The origin of this Wasserstein metric is actually L2 Wasserstein metric of probability measures. So given two probability measures, mu and nu, on the underlying space is Euclidean space R to the M with finite second moment. Then the L2 Wasserstein metric of mu and nu is defined by infimum of square root of integral of square of the norm x minus y over the coupling pi of mu and nu. The coupling means the given two probability measures mu and nu are marginals of this coupling. So then, well, it is very difficult to compute in general, but if we consider Gaussian measures, then we can find there it's an explicit form, because Gaussian measures are determined by mean and covariance matrices. So let us consider two Gaussian measures mu nu with a mean 0 and covariance matrices A and B. And their L2 Wasserstein metric coincide with square root of trace A plus B minus 2 times trace of square root of A power 1/2 B A power 1/2. So this is a metric. So if you divide by square root, still it is a metric. So I denote it as dW. So dW is actually a Bress metric, because if we consider the density matrices, this is exactly the same as square root of 1 minus fidelity. So in this sense, we also call it the Bress distance. So combined together, so Rajendra Bhatia says that it is a Bress-Wasserstein metric. And also, it is a Riemannian metric. So Riemannian metric means on the tangent space at each point, we have a certain inner product, and using the fundamental process to find the Riemannian distance, we can find a metric there. And it is coincide with the Wasserstein metric dW. So on the tangent space at a point A, what is the inner product? So for two tangent vectors y and z, the inner product is given by the sum of lambda I times real part of yij, gij. So these are the entries of tangent vectors y and z, and over squares of lambda I plus lambda j. where lambda i's are eigenvalues of the fixed point A. And they also found the explicit form of geodesic connecting two points A and B. The explicit formula is given by 1 minus t square A plus t square B plus t times 1 minus t times the symmetrized products of A and A inverse sharp B. And in my slide, I denote it as A diamond TB. So on the setting of the positive definite Hermitian matrices equipped with the Wasserstein metric, we can consider the following minimization problem. But unfortunately, Wasserstein metric does not satisfy semi-parallelogram law. So that means in this setting, we don't have Hadamard space. So we cannot apply the Sturm's result. But our objective function, denoted as g of x, is strictly convex. So we can apply the optimization theory. Okay, so then we have a unique minimizer. So how can we find such a minimizer? We can just vanish the gradient of this objective function. And then we can say that this mean, least squares mean, coincide with unique positive definite solution x of the equation identity equals weighted sum of x inverse sharp aj. So we call this the Wasserstein mean and denote as capital omega. And in this equation, Wasserstein equation, we take a congruence transformation, and two-variable geometric mean is invariant under congruence transformation. So this equation is equivalent to x equals weighted sum of square root of x to the power 1/2 aj x to the power 1/2. For more detail, you can find the following reference. And there is one approach to find Wasserstein mean. I say it is an iteration method. So for the given point, initial value, x0 is a positive definite Hermitian matrix. We consider the sequence as r plus 1, which is given by the map K of SR inductively, where map K is given by here. So we take the a to a power -1/2 from the left and from the right. And in the middle is a square of this weighted sum. And there is consequence is that this sequence SR converges to the Wasserstein mean. And the second property is that for all natural number R, we have the following treasure inequalities. So now what are the properties of Wasserstein mean compared with the Cartan mean? The first one is if variables commute, then Wasserstein mean is equal to square of weighted sum of aj to the power 1/2. And second, the Wasserstein mean is homogeneous. So homogeneous means we multiply the same positive scalar alpha on variables. It is equal to alpha times omega. Third one, the Wasserstein mean is invariant under permutation. That is the same as Cartan mean. Unfortunately, the Wasserstein mean is not monotone for Lubner order. So we can find just simple example. And the fifth property is the Wasserstein mean is invariant under unitary congruence transformation. And sixth property is that we take the determinant of Wasserstein mean. That is greater than or equal to the geometric mean of positive scalars determinant aj. And equality is satisfied if and only if the variables should be the same. The last one is the Wasserstein mean is less than or equal to arithmetic mean. So one can ask that, what about the harmonic mean? Unfortunately, the Wasserstein harmonic mean inequality is not satisfied. But recently, I found a lower bound of Wasserstein mean. Its lower bound is a 2 identity minus the weighted sum of aj to the power inverse. And also using this boundedness of Wasserstein mean, we can obtain that the extended version of Lee-Trotter-Carter formula. So which means we take the s power on the variables and compute the Wasserstein mean and take the power 1 over s. And its limit is equal to log Euclidean mean. Okay, now, so we have seen the Wasserstein mean of positive definite Hermitian matrices compared with Cartan mean of positive definite Hermitian matrices. So now, what about operator extension of Wasserstein mean? It is not simple because the same as the Cartan mean, we don't have the Wasserstein distance on the setting of positive definite operators. So similar to the Kachar equation, I attack the Wasserstein equation actually. So for two variables given a and b, and the weight t is in between 0, 1, we consider the two variable Wasserstein equation. So identity equals 1 minus t times x inverse sharp a plus t times x inverse sharp b. And we can solve this equation and we obtain that there is a unique positive definite solution. And the solution form is given by geodesic form, which is the same as two variable Wasserstein mean of positive definite Hermitian matrices. And the main idea of this proof is just Riccati lemma. So Riccati lemma means two variable geometry mean A sharp B is the unique positive definite solution X of Riccati equation, X A inverse X equals B. So the proof is not difficult, but the importance is this provides two variable Wasserstein mean of positive definite operators. So if you want to see the detail and the more properties, I want to give you the following references: 2019 and JMAA, and 2022, so Mediterranean Journal of Mathematics. But my recent research topic is, what about the multivariable Wasserstein mean of positive definite operators? So, well, I tried several times and with my postdoc, but still it's very difficult. So my idea is just attack the Wasserstein equation of multivariables, but I don't know. I don't have any idea about this. Thank you. Thank you for your attention.
Yeah, thank you very much for your interesting talk. Do you have any questions for our speaker?
I have a quick question. You
Yeah.
mentioned that the problem is very difficult. In what context you think it is very difficult? Is it the analysis part or the algebra part or the geometry part?
You mean the last
Right.
slide here?
Yeah.
Well, so left-hand side is identity,
Yes.
and right-hand side is the weighted sum of X inverse sharp AI. Is that right?
Right.
And well, one can, so on the setting of positive definite Hermitian matrices, the Rajendra Bhatia have used the Brouwer fixed point theorem. So I tried to use also same fixed point theorem on the setting of operators, but one can check that existence, but uniqueness is not satisfied there.
I see.
In the setting of the infinite dimensional case, I think that's the most difficult part, I think.
I see. All right. Thank you.
Yeah.
Do we have anything else for our speaker? I just wonder, like, in your slide right now, you have x minus 1 short A and then x minus 1 short B. It seems like, is there any connection between this and the spectral geometry? Because in the definition of spectral geometry, you also have kind of, A negative 1 and then short B and then 1/2, right? And A and then so on. So I see the components in the definition of A of the mean right here.
Oh, you mean in this slide, this equation?
Yes. I just wonder if there is any relation between this and then the spectral geometry. Because you see, even in the one, right? The equation has a unique positive definite solution of the form. So the second part of the form, like there, if you take the geometric mean, I mean naive geometric mean of that, right? You get a spectral geometric mean. Is that correct?
You mean you replace the geometric mean sharp by
the one in A times A negative 1 short B plus A negative 1 short B and then A.
Could you say again?
I mean the solution of the equation.
This equation?
Yes, the equation there, and then the solution, X solution, and then the second
solution.
part. Yes.
Okay.
You see T times T 1 minus T, and then times A negative 1 short B plus A negative 1 short B and A. So if you take the naive geometric mean of those two terms, you get the spectral geometric mean.
I see. So spectral geometry mean is A inverse sharp B to the power 1/2.
Yes, power 1/2.
Multiply A and the same term here, right?
Yes.
Yeah, I think that's good question. I think so this term A times A inverse sharp B is similar to spectral geometry mean.
Yes.
Yeah, so they might have a certain eigenvalue relation between the Wasserstein mean and the spectral geometry mean, but I don't know about this term can be replaced by the spectral geometry mean or not. This is actually symmetrized product, right?
Yes.
Yeah.
But I was thinking because like we have spectral geometry, and as you say in the equation, sum of omega I and then x short tai equal to x. So if that, I think that was considered in Lehman-Panfa paper in functional analysis. And they consider that matrix equation for geometric mean. So I just wonder if we can do the same thing for spectral geometry.
That is a good question, right?
And and of course we might do that for the weighted spectral geometric mean too.
Right.
I think that would be very nice. It's some kind of but I will look at it closer.
But But one thing that I want to say that is that compared with the metric geometry mean, the spectral geometry mean doesn't have the nice properties.
Yeah.
Because the metric geometry mean has like a contractive property, like for the Thomson metric, but the spectral geometry is not actually. But that I think that I agree that replacing like a spectral geometry mean in this equation, I think that is a nice project. I think.
Yeah. So we talk with you about that maybe in the near future.
Right, in the later, yes.
Yeah. Okay. Thank you. So do you have anything else for our speaker? I see. Let me see. He's still there or not?
I think Hoa and Tinyao Tam are familiar with these contents. But I don't know other people. So.
I see Dr. Patrick Joseph. But do you hear me, Joseph?
Yes, I'm here.
Okay, nice
Hello?
to see. Yes.
Yes. We also have a similar approach to the Kubo domains, and we made a general Wasserstein distance when we take the distinction of arithmetic mean and the general Kubo mean. And we proved with Daniel Virostek that it's also divergence, and we called it generalized Wasserstein divergence. And I have seen that there is some similar thing here, and we also computed the barycenter with respect this divergences. Maybe do you know this article?
So what is a generalized Wasserstein divergence?
The arithmetic mean minus Kubo mean.
Okay.
Arbitrary Kubo mean. So not just the geometric mean, because you have used here the Wasserstein divergence as arithmetic mean minus the geometric mean, as I seen. But you can take the arithmetic mean minus Kubo mean, general Kubo mean, and we have proved that it's also divergence with very good properties.
Yeah, I saw your paper in letter of math physics, right?
Letters in mathematical physics, yes, letters in mathematical physics.
Yeah.
I'm sorry about that. There is some problem with my camera, and I can't show my picture, but maybe you can hear me.
Yeah, we hear you well. Yeah, I understand what you mean. So basically, yeah, we might replace the geometry by the general Kubo domain. And
and we also computed the barycenter with respect this generalized Wasserstein divergence.
Yeah. And then in that paper, you also consider geometry mean the solution of that for n matrices. Is that correct? As I remember.
Yes. We also use it, but we also have another paper where we also give a generalization of arbitrary Kubo domain for n operators with weighted with the help of the barycenters. So if you like, I can send these articles if you want.
Oh yes, please. Yeah, you can just reply, to the email about seminar, so everyone would get that.
Okay. Maybe I will find it and I will send you.
Thank you.
Thank you very much.
All right.
So it was very good. I enjoyed very well this talk. Thank you very much, Professor Sejong.
Thank you.
So very good.
Yeah.
Thank you.
I think you know much contents in my talk. So
I am not sure, but it was very good for me. Thank you.
yeah,
I enjoyed
thank you.
All right. So I think it's too late now for Dr. Kim. It's almost 12 a.m. So I
Well,
think
this is nice time to study.
Yeah.
My
Yeah.
family slept. So
Yeah,
went to
yeah.
bed.
So